Welcome to This Explainer. Today, we're tackling one of the absolute most critical and honestly uniquely challenging junctions in any power plant, where the generator meets the transformer. You see, a generator-transformer block fault doesn't behave anything like your run-of-the-mill transformer fault. Why? Because you've got a massive rotating machine actively pumping energy into the fault for literally as long as it keeps spinning. This rotating to static interface demands the absolute fastest, most sensitive protection in the entire plant. So let's look at why your standard protection philosophy just isn't going to cut it here. Okay, let's dive right into this with a quick scenario. Imagine a fault occurs right at that generator-transformer interface. Your relay does its job and successfully commands the grid side breaker to open. Is the fault actually cleared? The answer is a massive, resounding no. It's really easy to think in terms of static grid isolation, but we have to remember a rotating machine is still involved here. The generator is going to continue supplying fault current through its own excitation system. Full fault clearance requires a whole lot more than just a single breaker clicking open. Here's how we're going to break this down today. 1. The hidden danger. 2. The fire hose effect. 3. Physics of core damage. 4. High-speed detection. And finally, 5. Coordinated master trip logic. All right, let's jump into section 1, the hidden danger. Engineers who are new to generator protection sometimes make a really dangerous assumption. They try to apply a transformer-only protection philosophy to a generator-transformer block. Think of the grid as a water main, right? When a fault happens, opening that grid breaker is like instantly shutting off the main valve at the street. Boom, water stops. But the generator? The generator is a fire hose. Closing the street main doesn't stop the water that's already in the hose, and more importantly, it doesn't stop the pump behind it. The generator literally doesn't know the grid breaker opened. It will happily just keep feeding that fault until the machine itself physically winds down and is explicitly told to stop. Which brings us right to section 2, the fire hose effect. Let's actually look at the timeline here to see how this builds. Bam! A fault occurs at T0 milliseconds. The relay detects it, and the grid breaker opens super fast. Let's say at T plus 50 milliseconds. Now, from the grid's perspective, the fault is totally isolated. But the generator's fault current contribution, that can persist for multiple seconds after the grid disconnects. Because the generator has its own independent excitation system, the fault current shifts as the generator's reactance moves from subtransient to synchronous, but it doesn't just stop. So you've got tens of milliseconds for grid clearance versus multiple seconds of continued generator feed if the excitation isn't actively removed. That is a staggering difference in the total amount of fault energy delivered to the core. So what does this actually mean for the hardware? Section 3, Physics of Core Damage. We engineers often obsess over whether a relay tripped, but the physical equipment, it only cares about how many milliseconds passed before the interruption. Think about touching a hot stove. Pulling your hand away instantly versus, say, a half second later makes an enormous difference in the burn you get, even though both feel fast to us. It's the exact same for a transformer core. A fault cleared in 50 milliseconds delivers roughly half the thermal energy of a 100-millisecond fault. Why? Because energy scales with time at constant current squared. Every single millisecond that generator continues to feed the fault is just compounding the thermal and mechanical stress on your equipment. If we don't shut down both of those sources instantly, the escalation is absolutely brutal. A single shorted interturn fault deep inside a transformer winding, which, by the way, might initially only produce really subtle differential currents, can escalate like wildfire. First, we see rapid thermal runaway and mechanical deformation of the windings, purely driven by magnetic forces. Within seconds, this internal arcing gets so incredibly hot that it actually vaporizes the transformer oil. That leads to massive gas accumulation and, if left unchecked, catastrophic tank rupture and fire. We are talking about going from an electrical nuisance to a massive mechanical and chemical disaster in seconds. Okay, so how do we catch this in time? Section 4, high-speed detection. Enter differential protection. In plain English, this protection stage has one primary job. Compare the current entering the protected zone with the current leaving it. If there's an unexplained imbalance, it means there's an internal fault, and it trips. Differential protection is hands down the fastest and most selective way to detect these issues because it completely ignores harmless external surges or faults outside of its zone. It is looking purely at the health of the generator transformer block itself. Now, because we are dealing with two totally distinct sources, the static grid on one side and a spinning machine on the other, This differential protection has to be incredibly sensitive, yet perfectly stable across both current sources simultaneously to prevent a false trip. It requires highly tuned millisecond-level calculations. If your system is even slightly misaligned or incorrectly interprets an external surge, you could trigger a nuisance trip. But if it works properly, it's a remarkably effective safeguard capable of catching those internal imbalances way before they have a chance to escalate into total mechanical ruin. Which leads us to the final piece of the puzzle. Section 5, Coordinated Master Trip Logic. You see, all of those advanced protection stages have to converge into a coordinated master trip. Look at these 4 mandatory steps. 1. Detect the fault. 2. Trip the grid breaker. 3. Trip the generator breaker. And 4. Initiate field de-excitation. If your differential protection detects a fault in record time, but your master trip logic only sends a signal to the grid breaker, you have completely failed to protect the transformer. You absolutely must hit all these breakers and the excitation system to fully isolate the fault from both independent sources. No exceptions. But wait, what if you send that trip command and a primary breaker just mechanically fails to open? You can't just issue the command and cross your fingers. You must actively verify the generator breaker status and confirm field de-excitation as a strict part of the trip sequence. If you don't verify that the isolation sequence actually completed, you risk leaving the fault energized indefinitely. This verification acts as your critical safety net to ensure that a single stuck mechanical contact doesn't result in a vaporized transformer tank. As we wrap up this explainer, I really want to cement the ultimate takeaway for your commissioning and plant reliability teams. Never assume tripping the grid side breaker alone has cleared a generator transformer block fault. You must verify the generator breaker status and the field de-excitation. Any protection scheme at this interface has to be designed assuming both sides can independently sustain the faults. So I'm going to leave you with this question to chew on as you review your own relay configurations. Is your master trip logic truly clearing the fault from all sources, or are you just shutting off the water main while the fire hose keeps pumping energy straight into your transformer core? Thank you so much for joining me in this explainer, and I hope this gives you a sharper, more focused lens for approaching generator transformer block protection.